Alright guys, we're going to take some notes, so pull out some paper for me, okay? We're going to do some examples. What I said, laptops and phones. Just let them have their batteries. Don't save their batteries until we need them. What did I say about the laptops once again? Why? Okay, can you see? Alright, so our whole new topic is about bonding, but every single thing we talk about today is referencing periodic trends, electronegativity, ionization energy, valence, electrons. It all is so dependent upon the last unit. I'll keep reminding you of the pieces that it's related to. So with bonding, we know all about bonds now. We know the properties of ionics versus covalents versus metallics. But now we're going to get to the nitty-gritty, like why exactly do they bond? And what do they look like when they bond? And then we'll relate the properties back to why they occur with these different compounds. So I'm going to tell you, I think, the key points here. And what I'm saying is probably sometimes more important than the verbatim words here. So if I'm a fast note taker and I'll write everything down, by all means do it or print these off beforehand. But the most important things you should be seeing here is, one, every single compound forms because they want to be more stable. Just like you, if you're high on caffeine and sugar and you're crazy high energy, you're not a stable person. You probably get moody whenever you have all that energy in your system. So you're not a stable person. So it's you're in your chill state and you're in your low energy state. You're much more stable. That is also true for compounds. So bonding is an energy lowering process, which means that the process of bonding will stabilize. Well, yeah, the atoms will become stable over time. And that's better for the atoms. Once they're stable, they're more happy. They have a low energy system. It's better for them in the end. So as these particles attract each other, there's a little bit of attraction going on from one side, a little bit of attraction going on from the other side. Boom, they're both more stable. Boom, we have a bond. Ionic bonds or covalent bonds both work this way. So as this bonding is occurring, in the end, there's going to be octet, 8 valence electrons around each atom. That can be achieved in multiple ways. Either you can gain or lose electrons to get octet, or you can share electrons to get octet. The situation where you gain and lose electrons is what kind of bond? Ionic, and you share electrons, it's covalent. So we know that those are two different types of bonds forming, but it's all happening because of the energy stabilization that has occurred. So give me the simple reason why bonds happen. To be more stable. And when they become more stable, they have attained octet. That is the main point here. I'm moving on. Okay. So this is on your chart, right? You have a lot of stuff that you've already put on your chart. So I'm just going to use some of the highlighted ones because they were, not everybody mentioned these, but as of yesterday, you guys added some more to it, so you should be fine. So electrostatic is a term we like to use with ionic. Electrostatic refers to what? Ions, yes, but electrostatic. Talk first and think if you can, see if you can come up with the definition of electrostatic. Or a description. Talk first. All right, come back to me. 3, 2, 1. I heard static as in like, oh, electrical shock static. Not the same thing, guys, okay? Electro refers to what, do you think? Electrons, right? Okay? And static, if somebody's static or something is static, it means it's not moving. It's stationary. It's there. It's not mobile. So static means I'm gonna put stationary. I don't know if that's the best way, but electrons are stationary. So that means electrons on a cation are staying where they are, and electrons on an anion are staying where they are. So the electrostatic nature is that I'm charged and you're charged, but what happens between positives and negatives is there's attraction going on. So that attraction is what we call the ionic bond. Is it really a physical bond? Is it like an atom is touching and goes, we're bonding? No, it's just like an attraction between two different charges. That's all an ionic bond is. And then because of this electrostatic charge, it's got a super, super, super strong attraction for each other. So that is a very, very strong attraction. And because it's so strong, it creates all of these properties like high melting point, high boiling point, let's say solid at room temperature, lattice structure. So all those properties come because of that strong attraction. Give me a thumbs up if you put down soluble in water. Good on your chart. If you remember, if not, maybe make a note to yourself. And then electrolytic means that it can conduct electricity. And it can only do that in two situations. So this is an example of an ionic lattice. Okay, so you've got green negatives and gray positives, green negatives, gray positives. So there's this great like lattice structure is what that actually looks like. So what's happening here is if I throw electricity at this, the electricity will stick on one and it won't move because the electrons are static. They're where they are, they're not moving. But once I put this in water, what happens to it? It breaks apart, right? It disperses. I'm not going to break this apart. This thing takes forever to rebuild, okay? But it breaks apart. And so what it can do is in water, you've got ions floating around separately. Okay, I'm going to put another negative. So as the electrical current comes through it, electricity comes through, it can bounce from ion to ion, ion, and it can move through in a current-like pattern. It can't do that in the solid state, so it's only electrically conducted in two states, liquid and aqueous. Liquid has another name, starts with an M. Say again? Molten, right? Liquid or molten state is what that means. Aqueous, AQ, means dissolved in water. Molten is one, aqueous is the other. And that's with ionic. Those are just a couple of key characteristics that we need to emphasize. And then with covalent, kind of countering what we just talked about, ionic was electrolytic and aqueous or molten state. Covalent is never, ever, 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 ever electrolytic. So it will not conduct electricity or heat. And what's the word volatile mean? Say again? Able to turn to a gas very quickly, so it's vaporizing very easily. That is a word that we've mentioned, I don't know, 4 or 5 times now. It vaporizes easily. And then we're going to talk about these molecules actually having shapes. So these are going to form true molecules. Ionic bonds don't form molecules. The word molecule actually goes with the covalent term. So these molecules will have different shapes. They'll be bent, there'll be a tetrahedron, there'll be a pyramid, they'll have all these shapes, and those shapes are going to be defined based on this thing called the Vesper theory, which is going to be our main topic for maybe late today or tomorrow. Okay? Alright, so this is a review of properties. Can I move on? Because you guys have this under your belt like crazy. You guys did a great job back there. Alright, so remind what this is called again? Lattice structure, right? So one thing that you can imagine is that this can break. It can shatter because of this the cleaved edges that you can see. So it can actually break perfectly right there or right here. And we take advantage of that because who actually puts like a huge cube of salt, sodium chloride, on their fries? Like huge cube. Anybody? No, what do we put? Little teeny tiny crystals. Well, there's still that structure. There's still like ions like that going together, but they've been cleaved in such a way they're tiny crystals now. But they're still crystals. There's like particle life. So we've seen that in real life, but it's just not that scale. All right, so take a minute and talk to your partners about what you noticed here. All right, so what do you guys notice? Oh, what about the valence electrons? They're represented by red dots. Okay, so these are called Lewis dot structures. Who's ever heard of a Lewis dot structure? Maybe 7th grade, by accident, your teacher's like, let me give you more chemistry than you need to know. Okay, so that's what they've done. Essentially, what this guy, Dr. Lewis, did was he represented the valence electrons that all these elements have as dots. So if you're in group 1, you have how many dots? If you're in group 7, you have how many dots? Okay, so we essentially are now representing valence electrons as little dots. Why do we care about the valence electrons and not the inner core electrons? Yeah, if you're going to bond, it's only going to be with valence electrons. So that's one thing we care about. Valence electrons are the electrons that bond, aka that makes them reactive. So valence electrons are the reactive ones. The other ones don't do nothing. They sit on the inside of the atom and they just chill. They're attracted to the nucleus and they don't do anything. So the valence electrons are the reactive electrons. Hence they bond. So that's what's so important about valence electrons and knowing a lot about them. But what you guys did, you did pretty well. I'm not quite done grading for your response, but so far so good. A couple of light questions that were a little off, but these were fine. Okay, so when we're looking at ionic compounds and drawing their Lewis dot structures, this is what it looks like. Let me show you this first. Okay, so why does sodium have 1 dot? 1 valence electron. Why does chlorine have 7? And then what is a metal and a non-metal likely to do when they bond? They form an ionic bond, which is that shared or is that transferred? Transferred. So what you're seeing is that sodium has transferred its single electron here to chlorine, and in that transfer, they formed charges, positive and negative. Okay, I want you to write down this example. I'll leave this up here so you can read a little bit more too. So the title of what this is dot structures for ionics. Lewis dot structures for ionics. So the thought process behind a drawing of an ionic Lewis dot structure is that you first must draw the individual dot structure for each element, which is what we did here. We did sodium ion, or sodium, and then chlorine with their individual valence electrons. And then our second thought was okay, octet is the rule. How do I get somebody to octet? What's going to happen? Who's going to trade electrons? So we all know that metals tend to lose electrons, and nonmetals tend to gain electrons. We've talked about that, for about a week. We've seen this happen, but now we see it in action, and it's because sodium. Look at sodium. Tell me about its electronegativity compared to chlorine. So put your finger and think about the periodic table. Who's got a higher electronegativity? Chlorine for sure, right? Who's got a higher electron affinity? Chlorine. So double whammy. Chlorine is certainly going to be taking away sodium's valence electron to give it to itself to make it octet. Sodium bounces back to the octet it previously passed, which was whose electron configuration? Neon, right? Sodium, back it up, 1 is neon. So that means its electron configuration is octet because neon has octet. So they're both happy, they both have octet, but what we now see is that sodium has formed a cation and chlorine has formed an anion. And with that, we draw brackets around the chlorine to indicate those are 8 electrons around chlorine, no longer around sodium. And if I don't put a number here, what do you assume is here? 1s, okay? So let's do the same thing, but for magnesium oxide, MgO. So step 1, do what? Individual elements and their dots. You might need periodic table out. Put Bryce on board. Thanks, Bryce. All right, give me started. What'd you draw first? Magnesium with 2 dots. Jacob, next. Oxygen with 6 dots. For now, it does not matter where we put these dots. Just make sure it's 2, 2, 2, 2, if you're going to draw it that way. Bailey, what do I do next? What do you mean?
Well, draw an arrow.
This arrow? Okay. Okay, so you're saying magnesium transferred its dots to oxygen. So I like to make sure we keep using that word transfer and not share. So it's transferring its electrons to oxygen. So it makes magnesium with no dots and what? Hold up. What does magnesium have on it now? 2 plus charge. Okay, Cole, what's next? It's wonky. There's 8 dots there, guys, okay? Brackets and what? -2 because it forms a -2 charge. Yay! All right, we're doing good. And again, relate that to electronegativity. Magnesium and oxygen, who's higher electronegativity? Oxygen. So therefore, it takes the share, or it takes the transfer of electrons. Can I go past this? Show you guys something. Okay. All right. So looking at this one, talk to your partners. Answer those questions. And write this example down, this example right here. I heard you say the key word, which was? Okay, covalent and share. And nonmetal. Look at all these fun facts. Really, every single thing, every single one of those facts matters. This is a nonmetal. This is a nonmetal. Nonmetals come together, and they do not make ionic bonds. They make covalent bonds, and we show that differently because do we show a transfer of electrons? No, what do? They scooch together like, okay, chlorine 1 and chlorine 2, we're going to pop these electrons between us. We're going to pretend that I own both of them, and the other one's going to pretend that it owns both of them, so it looks like they both have octet. So I'm going to show that a little clearer here. I'll get my marker to work with me. So chlorine 1, if I circle what's around it, how many electrons are around it? 8 octet, right? If I circle chlorine 2, how many electrons are around it? 8 octet. Now, truly, there's not 16 dots here. How many dots are there? 14. So I'm not showing they both individually have octet. I'm just showing that together as a bonded situation they have octet each. So those 2 shared electrons in the middle are counting for octet for both parties. And why would they tend to share based on electronegativity for this situation? They're the same. So they have the same what? Electronegativity. So if they have the same EN value, no one's going to win that tug of war. No one's going to get more electrons than the other. So they have to share equally. Okay, so write down same electronegativity value means they have to share equally. And the equal word is really the key part here. And I want you to consider how that would differ for HCl. So try to draw out, just like you did up here, 7 valence plus 7 valence makes this. Draw that for HCl. Like how it would form. So again, you're starting off with single elements with their dots. All right, Bryce, what did you start off drawing?
I did the H with the dot.
Single dots, it's first group, right? And
then plus chlorine with the 7 dots.
7 dots on chlorine. Okay, keep going.
And then I did an arrow. And then I did H with dots to the right. And then chlorine with 6 dots on the first side of it.
And you're good, right?
Yep.
So in this case, guys, circle who has octet. Who has octet? Chlorine, right? So we've got chlorine, it's got octet. So chlorine is happy. Now, I told you octet is the rule. Well, you know, sometimes we have caveats to rules or some exceptions to rules. Just like if you gotta use the bathroom, you gotta let me know. But if you've gotta use the bathroom, just like you gotta know the exception to that rule, right? There are exceptions to this rule too. Octet is on chlorine, has to have octet. Now, hydrogen only has how many? 2. That's called duet. Duet means what? 2. Look how teeny tiny hydrogen is, right? Look at it. There ain't no way it's going to get octet because it would have to gain how many electrons? 7. Hydrogen doesn't have the capacity for that because it only has a 1s shell, which only holds 2 electrons total. So it just can't get octet. It's teeny, teeny, tiny. So it's cool to have 2 valence electrons around it. Hydrogen and like maybe 1 or 2 others are going to have exceptions to the octet rule. So generally octet is a rule, but this one is one exception. All right, so who's more electronegative, hydrogen or chlorine? Who? Okay, so hydrogen's here, chlorine's here. Chlorine's more electronegative. So instead of drawing these as 2 dots, you'll never see this past right now, me drawing 2 dots in the middle. The way that I would normally draw this, and you will too, is a line. That line represents those 2 dots. So how many electrons does a line represent? 2, right, 2 electrons. So line, chlorine, and then these dots are still here because those are called lone pair. They're non-bonding electrons. They don't bond, they're just chilling on the outside. The bonded pair are the ones that are holding the 2 together. So what we're going to show here together is that, all right, I know there's 2 electrons here, right? But who's going to pull the electrons closer to themselves because of the electronegativity differences? Who? Chlorine. Chlorine is more electronegative. So there are 2 electrons here. We know that. But what they're going to do is they're just going to shift this way a little bit, just a hair, because chlorine is more electronegative and hydrogen is less electronegative. So they're still sharing. Like, I can give Kendall, we have 20 cookies to share between us. She's like, I'm chlorine, I'm going to take on 18 cookies, and you can have 2. Like, we still shared 20 cookies, but did we share equally? No, that would be a 50-50, 10 cookie split here. This is not an equal sharing. So what we're going to talk about more in depth is the difference between equal sharing and unequal sharing. So equal sharing and unequal sharing create 2 different types of covalent bonds. Give me a thumbs up when you're good here. Okay, so to get a really good grasp on equal sharing and unequal sharing, you might need your laptop. Let me see how many of these I have first. So there's a polar bear, and penguin. Go ahead and pull up. Go to my website, okay? That's just for you to leave. I will pass out some of these. I have copies. Go ahead and go to my website, and I'll show you guys what you're doing. Because I only have like 12 of these. So you don't have to share. I'll show you this is on my website too. So before I start going into depth about like the application to chemistry of this, I want you to see this in a kind of a cartoon setting because it actually makes a whole lot of sense. So when you go to homework, I try to link, classwork under homework just because you can find everything in the same place. It's easy for you guys. Today, Wednesday 28th, classwork link, polarity reading and questions. I'm going to see where we are in about 15 minutes. But when you click that, this polar bear penguin reading comes up. And do just skip the questions for the moment because you won't know how to answer these questions until you read. Okay, so start with reading and then go back and answer questions. Okay, and you can talk to your partners, talk to your group mates. I just passed out a couple if you want to start reading now, but you can access it here. Polarity reading. Definitely, I would write on thinking about that because this is actually building your understanding of what polarity means. Huh? You gotta pay attention. You gotta pay attention. So if you want a paper copy of mine, do not write on that paper copy. Like I said, you'll answer the questions in your note sheets. I'm going to ask for us to do the questions together. That way we can clarify. You can hunt through the reading for some of these, because I only want to do so many of these because I'm going to talk more in depth about it. So question 1, how does the comic book define a polar molecule? Talk for 30 seconds. Can you find it? All right, mutual stable, polar molecule, and I'm expecting that you're writing some of this down in your notes. Okay, so polar molecule, go.
It's a molecule with a difference in charge.
All right, so difference in charge on the molecule. So I'm dumbing the definitions down some so we can get like the basics, okay? Define electronegativity based on the first 2 pages. We all know what the electronegativity is. I'm moving past that. We know that's just, well, maybe let me clarify what that means. Bryce's table, what's electronegativity mean based on the reading?
How well an atom can attract an electron to itself.
Okay, so how well an atom can attract electrons. Okay, we know some things are very electronegative, meaning they're super greedy for electrons. Others are not so electronegative. They could care less about attracting electrons towards itself. And I'm going to skip the trying part because we know that already. Number 4, what is the artist trying to represent when there are 2 polar bears arm wrestling together or 2 penguins arm wrestling together? Non-stable. Okay, good. So the 2 polar, I'm going to say it's 2 bears or the 2 penguins, the same situation occurs, and you're saying the same electronegativity value kind of thing, like same level of attraction. So you guys tell me, if you had 2 polar bears in that example or 2 penguins, and they had the same electronegativity value, they termed this later on, maybe in the comic or maybe right there. What kind of molecule is that? Ariane, what kind of molecule is that? Non-polar, right. Okay, so non-polar. That is a non-polar molecule as it stands. So, reminder, polar means a difference in charge, meaning difference in electronegativity, or big difference in how these electrons are distributed across a whole molecule. So if you have the same electronegativity value on both atoms, does it cause any disruption to how electrons are shared? No. So electrons are evenly distributed. So Kendall gets 10 cookies, I get 10 cookies, evenly distributed. So that means that it's non-polar because there's no difference in how the charge is distributed. Non-polar molecules have the same electronegativity value. All right, so what are the 3 types of bonds? And what happens to the bonding electrons in each type of bond? So the 3 types of bonds, Ariel's table. Some of you started. Ionic. So now the covalent, look on that page. It says page.
Non-polar.
Right, so I'm going to go in order. What's the first one listed?
Non-polar.
Non-polar. I'm going to add one word to that. Non-polar covalent. Okay.
Polar.
Polar covalent.
And
And ionic. Yes, we know there's metallic, but that's a kind of separate category right now. Okay. So non-polar covalent, polar covalent, and ionic. And this is where I'm going to jump on my slides because it's a little bit easier for me to write over there. And we will come back to some of these questions here in just a second. Okay, guys? All right, so here's what I want you guys to write down from with respect to book number 4, what we were just answering. Or maybe it was number 5. Not sure. All right, so 3 bond types. Number 1. I want you to tell me, does the word equal or non-equal come into play with non-polar? Good. Who said that? Thank you. So non-polar covalent have equally shared electrons. Equally shared electrons. An example, like I think Cole was just saying, was the bear to bear or the penguin to penguin. An example would be like hydrogen bonded to hydrogen, or chlorine bonded to chlorine, or oxygen bond to oxygen, or nitrogen bond to nitrogen. I'm drawing these as like fake bonds for now, it's just a single bond, but they're showing equal share of electrons. All right, number 2 are the polar covalent bonds. Does the word equal or non-equal, not equal come into play? Not equal. I'm going to put unequal just because I don't like not equal. So an unequal sharing of electrons. This is basically a set of definitions right now. I didn't have you do reading guide 8, which is where some of this would have come into play. So pay attention closely here, okay? New information. Polar covalent bonds, unequal sharing of electrons. Why would they be unequally shared, CJ? Okay, good. So because of large electronegativity, or I'm going to say because of moderate electronegativity differences. So in that first one, why were they sharing fairly equally? Right, in all these examples I gave you, they have the same electronegativity values or same electronegativity, or we could also relate that to small electronegativity differences. Because you can have some examples where you have a little bit of electronegativity difference and it's still nonpolar. All right, then, ionic. Lastly, ionic, because it is a continuum. Ionic would be last here. Tell me about the electronegativity differences here. Small, medium, or large? Large, right? So a large electronegativity difference is going to cause an ionic bond to form because one is so super electronegative and one is totally not. One's going to be like, throw the electron over there, transfer it, you have an ionic bond. So this is like a very large difference. And generally this is between a metal and a non-metal. FYI, if you ever are concerned on, is it going to be an ionic bond or not? All right, give me a thumbs up once you get those 3 pieces of information down. Okay. So there's more to the story. This is like the simplistic manner. Go to the second link under homework. Second link. And it's HTML5, so it'll load if you just click play. You guys with me? Try not to move too fast here. So they have a couple of different systems. I want you to play. I just want you to play, explore how they note polar and nonpolar bonds, explore the electronegativity differences. Literally, take 5 minutes and try the 2 atoms, and then try the next, and then the next, so you can kind of sequentially go. Play with the factors, the variables that are involved. Talk to each other. We go back to the 2 atom system and let's play together here. So I want you to have an example for each style, okay? So 2 atom system, A and B. Let's make their electronegativity the same. So just put them right in the middle. And I'm showing bond dipoles and I'm showing partial charges and I'm showing bond character. I'll even show the electron density. Okay, so here we go. We have equal electronegativity difference. Tell me about the bond character. It's what? 100% covalent. It's like more covalent than it is ionic. Do you see any like arrow, like dipole moments? These little dipole arrows like that? No. Okay. So what kind of bond is between A and B? Loud and proud. I know it's covalent. What is it? Non-polar covalent or polar covalent? Non-polar covalent. So are they equal or unequally shared? Equally shared. So non-polar covalent, equally shared, and the electron clouds are both same size and everything. All right, so then change B to be more electronegative, and what do you notice? There are 2 or 3 changes that have occurred. First off, you tell me, Is this, are these electrons between A and B equally or unequally shared?
Unequal.
Unequally shared. Who's taking more than their share? B, why? Extra negative. Now there's a little notation, so we're all on the same page. If it is is this a polar covalent or a non-polar covalent bond? Polar covalent. If it is a polar covalent bond, you draw above the bond an arrow like this. It's called a dipole. Dipole moment. It's just an arrow. The arrow is pointing towards the more what? Electronegative one. So this one's more electronegative. This one's less electronegative. Okay? So since it's more electronegative or less electronegative, we're going to show the arrow differences. So what is the partial charge? You guys can barely see it on my screen. Do you see that? Showing a partial positive or partial negative? Negative. So on this side of the arrow, there's a partial negative. It's like almost an 8. It's a lowercase sigma. It's almost an 8, but not quite. Okay? So the arrow's the partial negative side. The hash mark kind of looks like the plus, right? So guess what charge comes over here? Partial positive. Okay. So this is a polar covalent bond. That bond right there, this one right here, with the 2 electrons in it, it's pushing that way, so the negative goes on this side, the positive goes on this side, because of the difference in electronegativity. I'm hoping that you're drawing or writing this down, or maybe just internalizing something, okay? So, if it's polar covalent, what do you have to draw? The dipole, sorry, that's called a dipole moment. That's what this little arrow thing is called, okay? And what should you note on the ends? The partial charges. They're not full-on positives and full-on negatives because we're not talking ionic yet. We're still talking covalent, so that's why it's a partial positive and partial negative. So what we have here, and this was like the second part of the reading, we have a problem. We have polar, and we have polar covalent. Those are 2 different terms, truly. The polar covalent bond is this bond right here. That is a polar covalent bond. But looking at this molecule, overall, this big old molecule, AB, you see one whole side that's partially negative and one whole side of the molecule is partially positive. So overall, the molecule is also what? Polar. But the molecule's polarity and the bond polarity are related. We're going to start to segregate those terms maybe more tomorrow. So what do you read a little bit farther? Polar molecules versus polar bonds. I wish we had different words, but we don't. Okay? All right, so let's go back to our notes. So halfway close your computer or all the way close it. And I'm going to show you what the important stuff is here, okay? So here are values to associate with those 3 types of bonds. So do that for me now. Write that down, please. I'm going to give you some old, disgusting pieces of papers that I've been using for like 8 years. Yes. All kinds of different ones. Please pass back. Yes, you pass. Go back to it. Take some plastic back, please. Take some plastic back. So this is a big old electronegativity chart, and I'm providing one for you. Sometimes the numbers are not agreed upon by scientists. But everybody look at hydrogen on that little teeny tiny periodic table I've provided you. Once you get it, pass them back to the guys at the labs. Okay, everybody look at hydrogen, and what does it say under hydrogen? 2. This one says 2.2, but on yours it says 2.1, right? So that is the electronegativity value for hydrogen. It's 2.1. What's it say for fluorine? Thanks. It says 4.0, right? 4.0 is the largest number. It is very, very electronegative. So if I put a bond between hydrogen and fluorine, I want you to be able to, like, qualitatively and quantitatively estimate, is that a polar covalent bond or non-polar covalent bond, or is that thing going to be ionic? Let's see. So draw out H-F. Let's write the number for hydrogen. What's the number for hydrogen on your table? 2.1. What's the electronegativity value for hydrogen, or fluorine? 4.0. Okay, what's the difference in electronegativity here? 1 point what? 1.9. So it's not negative 1.9. It's just it's the absolute value difference. So the difference between the electronegativity difference is 1.9. 1.9. Where does that fall in our? Where does that fall in our category? Bad example. Let me. It does fall in ionic. Okay, so I told you it was a continuum, right, from nonpolar to polar to ionic. These are two nonmetals. So what kind of bond should they form? Two nonmetals should form a covalent bond. It's a super, 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 super polar covalent bond. But that's why these are estimated values. So let me do another example because I just didn't think about that extreme difference. Let's do carbon. Scratch that. Let's do carbon and fluorine. So what you'll find is sometimes it doesn't match our scale, but it is a continuum. Okay. So carbon's number is what? 2.5. Okay. What's the electronegativity difference? 1.5. Okay. Where does that fall? Polar covalent. So, polar covalent. So on top of this bond, I need to draw a dipole moment. I need to draw a dipole moment pointing towards which direction? Fluorine, because it's more electronegative. And I put a little hash mark on the other side. Who gets the partial positive? Carbon. And who gets the partial negative? Because it's going to be partially negative due to that electronegativity difference. So that's what we're going to do first, okay? So I'm going to take another minute to make sure that you are clear. Oh, before I move on, do you notice on your noble gases, helium, neon, argon, maybe krypton, I'm not sure, they have no value on your papers? Why? They're already stable. So do they want to share electrons? Heck no. But what you'll notice that xenon and radon on your papers, do they have numbers? Yeah, so they're like, yeah, I'm willing to share if I have to. I have plenty of room for more electrons if anybody needs a bond with me. All right, so we just did that. Oh, what is this one representing? So again, polar covalent. Who's more greedy? Fluorine. And what is this one showing? Because it's equal sharing. This one's not equal sharing or unequal sharing. Okay. And yeah, I'll show you that in a second. Okay. So let's consider cesium with chlorine. I want you to write cesium dash chlorine, and let's decide what kind of bond it forms. Cesium is CS. It's in group 1. Cesium is CS. Right, so let's see. CJ's table, somebody tell me cesium's number. What is it, 0.7? And then front table, Meniere's table, tell me chlorine's number. 3 what? 0.0. Okay, everybody difference? 2.3. Where does that fall in our continuum? Ionic, right? So you know that this is not going to form an ionic bond. So I'm not even, I can draw that line there, but I might remind myself, line, that means covalent, so I don't really want to put the line anymore because I know that this is going to form an ion charge, and this is going to form an ion charge. Because ionics are metals and nonmetals, and then our electronegativity difference doubly supports our thoughts there. Let's do oxygen and bromine. O has what? 3.5. Bromine has what? 2.8 difference? 0.7. And where does that fall? Ionic, nonpolar, or polar covalent? And so if it's polar covalent, I put like PC over here to remember that it's polar covalent. This is ionic, like we said up here. What do I have to draw? Dipole moment pointing towards Y oxygen. Bigger number, more electronegative, hash mark, partial what? Negative and partial positive. Okay. And give me a thumbs up when you have you can determine polarity. All you gotta do is have this chart, right? You can estimate, like looking at differences, but this is a true value now you can have. All right.
And this is not right.
Okay. This will be the last slide we write today. If I don't get to explain it all today, I'll start with this tomorrow. Okay? Take a minute and write. Because this is the premise on how we draw every structure from here on out. Okay? So you need to have this stuff. So these are our rules for success. Bryce's table log off the computer and do that one. Stackers. Cole's table, y'all's laptops, log off. Jamia's table, log off, and put your laptop stuff on me, please. I'm doing one example for us as soon as I get laptops up. Start your laptop and then log off and put that up for me. Giving you guys some time here to write down. My reminder, if you are in AP, who's in an AP class? Have you all signed up for your exam? Who is not? Who's not sure? I'll show you how to do that in just a second. You gotta do the interventions. Today's the last day to sign up for the exam. All of your teachers have not said this. Okay, remind me in just a second. Okay, I will show you in just a second, okay? Alright, eyes back up here. So, if we wanted to draw a structure for methane, CH4, write down this example with me, okay? CH4 is methane. I would first total the valence electrons of the group. So I need to add up, so I'll get down to the bottom piece in a second, work with me on this example. I need to add up all the valence electrons that carbon and 4 hydrogens contribute to this overall structure. Everybody have fun carbon? How many valence electrons does it have? 4. Okay, so put 4, okay, plus 4 hydrogen. So how many valence electrons does hydrogen have? 1. Okay, so that's 4 plus 4 times 1, which is 4 plus 4, 8. 4 plus 4, 8. Got it. Okay. So our total structure here has 8 valence electrons that it can bond with. That's it, just 8. Choose a central atom. Carbon is not so electronegative. It's kind of like in that region, but it's not really that electronegative. It's willing to share with bonds all the time. So we're choosing our central atom. We're going to choose carbon. Okay, choosing central atom done. Bond all atoms to central atom with a shared pair of electrons. So all I do is I should see everybody working with me, okay? I'm going to show a shared pair here, to the left, to the right. I'm going symmetrical. I'm going to add on the hydrogen and add on the hydrogen. All right, so I've added on 2 of the hydrogens. How many do I have total? 4, so I got to add 2 more. So I'm going to add 1 on top and bottom. What does a single line represent? 2 electrons, right? Okay, so I've bonded all the atoms. Distribute the rest of the electrons to satisfy the octet rule. So who has octet? Carbon, right? 2, 4, 6, 8. Check. Hydrogen doesn't have octet. Oh no, what's the problem? Is there a problem? So hydrogen. So around carbon, there is 1, 2, 3, 4, 5, 6, 7, 8. There are 2, 4, 6, 8 electrons. That's good. How many are around each hydrogen? 2. Is hydrogen okay with that? Yes, because it can have duet. That's 2. That's 2. That's 2. And that's 2. Remember, they share. So hydrogen's happy and carbon's happy. So once I've bonded and made sure everything has octet, what I need to do is, I don't have any extra electrons, so none of the bottom of this applies to this particular one. I need to check and say, okay, I had a total of 8. How many do I have on my structure? 8, right? I'm going to clean this up. Oh, this is what it looks like. And I have 2, 4, 6, 8 electrons on my structure. I'm done. This was a very simple one. We'll do more complicated tomorrow, okay? All right, so I can't give you your homework because we don't know enough information yet. So enjoy your evening, okay? Because as you can see on here, it says Lewis dots drawn for lab. We can't do it yet because we don't know enough information, okay? Darn it. Poop. You guys can read the textbook.
Okay.
No, do not keep my electronegativity sheets. Keep all that in the middle of the table. Keep them all in the middle, okay?